lectures, Attosecond physics near future prospects, because each one is dealing with experimental capabilities that experimentalists claim they will have soon. And in my group, we have said, well, assuming they achieve what they're trying to achieve, what new physics will be observed? So that's the motivation for what we do. And in the first lecture, I told you what can be done and what can be learned if attosecond pulses become intense. Okay. This lecture is something completely different. I don't think anybody is in this field, but it will be a new area of attosecond physics, which is when one achieves attosecond pulses of electrons. My third lecture will deal with what can you do with circularly polarized attosecond pulses, but that will be on Saturday. So, as outlined, since this is new to most people here, I'm going to give some background and our personal motivation. And then show you what we did initially to treat ultrafast electron diffraction as a potential scattering, then to treat it correctly as coherent scattering, and then how to improve on results for coherent scattering with energy resolved scattering. But I go back to the title. The key motivation of attosecond physics is to image electronic motion. In the hydrogen atom, if you just use the Bohr model, you can easily calculate that an electron orbits a proton in approximately 152 or so attoseconds. So if you, and all chemical processes, when two atoms combine to form a molecule, or if you excite a molecule to make some sort of chemical transformation, the electrons are moving on a hundreds of attosecond time scale. The question is, can you observe such motions? That's a key motivation of attosecond physics and of this talk. So, let me, first of all, since this is electron scattering, we're looking at short electron pulses versus optical pulses, let me say that electron scattering is about 1 million times larger, has about 1 million times larger scattering cross-sections than photon cross-sections. So this is something that is valuable. Furthermore, for electron scattering, elastic scattering dominates. So we heard from Linda's talk that when you do at LCLS these X-ray scattering experiments, the idea is to image before you destroy. Because as I will show you, the X-rays really damage the targets, and but for electron scattering, the elastic scattering dominates, so you don't do as much damage. The spatial resolution is also better. For example, a 10 keV electron has a wavelength of 1/10 of an angstrom, whereas a 10 keV photon has a wavelength of 1 angstrom. So you have better spatial resolution. I don't know if you can see this. I had to transfer from one PDF file to another here, but this is a review in 2006, which is taking data from a paper in 1995, but it summarizes very nicely a key difference of electron versus optical pulses. That is, if you have electrons anywhere in the range from 80 keV to 500 keV, or X-rays of 1.5 angstroms, which corresponds to 8 keV of energy, the ratio of inelastic to elastic scattering events for electrons is about 3, whereas for X-rays it's about 10. So you get 10 inelastic scattering events for every single elastic scatter. Moreover, for each of the inelastic events, electrons deposit about 20 electron volts, whereas X-rays, if you absorb an X-ray in some event, it's 8 keV, so you absorb 8 keV of energy. And now, if you look at the energy deposited per elastic scattering event, which is what you want because that doesn't destroy the target. If there are 3 inelastic events for every elastic scattering event, for electron scattering you deposit about 6 keV in your target, whereas with X-rays you deposit 80 keV. So the energy deposition is much greater. Now, that said, there is an advantage to X-rays because the elastic mean free path for an electron is about, if you call that 1, then the mean free path for X-rays is about 100,000 to 1,000,000 times better, which means if you have thick samples, you really need X-rays to image it. Electron scattering is for thin samples, and so on, or isolated molecules. Our motivation is based on discussions with my colleagues at Nebraska. In 2009, which is when we started thinking about these issues, my colleague Herman Bachmann and Nobel laureate at Caltech, Ahmad Zewail, wrote a National Academy of Sciences paper on a scheme for producing ultra-short electron pulses. And the idea is very simple, that you shine a laser on some metal tip, for example. The laser is oscillating at 2.5 femtoseconds. And so every time the electric field is pointing this way, you get an electron pulse out from your metal tip. And that pulse is now moving with some energy. You've all studied first-year quantum mechanics, I hope. And you know that if you have an electron wave packet, what does it do as it propagates? It spreads. Okay? So you have a spreading wave packet, and that's a problem because you want a spreading wave packet means the time over which it overlaps a target is very big. And if you want to stop the motion of electrons in your target, you want your electron pulse to be very narrow in time so that you pick a particular instance at which you sample the target. That's where the electrons are moving. So what do? Well, in this paper, they proposed some scheme. I'm not an expert on how you would do this, but it would be some laser mode that you send in that with the electron pulse here, you have this Ponger mode of potential, and the slow electrons slide down this potential and get sped up. The fast electrons here, on the other hand, see this rising potential and they get slowed down. And so you have this pulse, and as it's moving along, the slow electrons are catching up, the fast electrons are slowing down. Right on the target, you have them overlap so that you have the narrowest possible electron pulse. And in this paper, my colleagues, they may have written another paper in which they developed a thin lens type formula to predict exactly where you put your target so this optimum condition applies. More recently, we hired another faculty member, Martin Centurion, from NPQ in Garking, and he also does ultrafast electron work, and they wrote this applied physics letters proposing some scheme of using magnetic and electric fields to compensate for the dispersion, which is a fancy term for getting this pulse to be narrow on a target. And this shows you how they use the fields to act on different components of a wave packet and then make them combine on your target to a narrow pulse. So, after discussions with my colleague Bachmann in 2009, I had a new graduate student and I said, look, this might be interesting. Suppose experimentalists succeed and make attosecond pulses. What could you see? Electron motion. So that's what motivated us. And of course, if you just want to see, if you're going to see anything, you do the simplest possible theory you could possibly do. You don't worry about all the complications, because if something is not going to work, you don't want to spend a lot of time on it. So we treated the electron diffraction in the simplest possible way. And because this was one of the first papers, of course, it immediately got into Physical Letters with a lot of discussion with the referees about taking into account variations of experimental parameters that made our images much worse than they were if we just assumed fixed experimental parameters. I'll show you that later. But the experimental setup we imagined that we tried to simulate was the following: that you have a laser and you have an atomic beam. And of course, for proof of principle, we chose an atomic beam of hydrogen atoms, because then we could work out a lot of this stuff analytically. And this laser pulse excites the hydrogen atom to a coherent state that beats. And I'll show you what that means in a second. So this coherent state is beating, and after some time delay, after you excite it, you hit it with the electron pulse, and you get a diffraction pattern for these electrons. They have an angle phi in the scattering plane, and they're scattered by an angle theta. These are the key parameters of our system. We're choosing 10 keV electron pulses because my experimental colleagues said, oh, that's very easy to do, to make. And we chose a pulse width of 110 attoseconds because that was one of the examples in the experimental paper proposing how to build attosecond pulses. For this energy, the wavelength of the electrons treated as waves is 1/10 of an angstrom. We assumed an angular divergence of our electron beam of 10 to the minus 3 radians, which is what my experimental colleagues told me is reasonable. And these are the two time-varying targets we chose. For hydrogen, we chose a linear, coherent superposition of the 3p and 4p state. And for the theorist's molecule, H2+, which Brett Esri fortunately talked about, we proposed a linear combination of the sigma Gerada 1s and the sigma Ungerada 1s wave function, which André Bandrauk had proposed to experimentalists as an interesting superposition. He never said how to produce it, and so we didn't either. But it was in the literature, and so we adopted it. For the hydrogen case, we gave explicit guidance as to how to produce this linear superposition. Because we wanted an equal population of 3p and 4p. And so it turns out if you use the 8th harmonic of a Ti-sapphire laser, that gives you an energy of 12.45 eV, which is right in the middle between the 3p state and the 4p state. You have hydrogen in 1s, one photon transition takes you to a p state, and this will take you right between the two. If you now plot the pulse, using time-dependent perturbation theory, you plot the pulse duration as a function, you plot the population of all the p states as a function of pulse duration, you find, you probably can't read this, but this is the 3p population, this is the 4p population, This is the 5p population. This is the 2p population. You see, if you take a pulse duration of about 8.7 femtoseconds, the population of 3p and 4p is equal, and the population of other nearby p states, 2p, 5p, is 0, essentially. So this is what we proposed. And then we use this simple firstborn that you learn if you study scattering theory still in quantum mechanics. It's not as often taught, but it should be. In firstborn, you treat the target potential as a charge density. You add up all the electrons in their state, and you scatter from this charge density, and you get this scattering amplitude, which is a Fourier transform. If you treat the incident and scattered electrons as plane waves, it's a Fourier transform of the charge density of your target, and you find that the differential cross-section for your scattering is the absolute square of this amplitude. That's the simplest possible theory for electron scattering. And this is what we get. This is as a function of time delay. So the time delay here means that the electron and the laser pulse have no delay. So this is what along the z-axis, this is the linear combination of 3p and 4p states, and this is the diffraction pattern. As you increase the time delay between the production and the sampling of the target, or pump and probe, make this t over 4, where the beat period of these two is about 6 femtoseconds. Then you get this diffraction pattern. If you have a time delay of half the beat period, this is what the charge density looks like, and this is the diffraction pattern. So what's happening here, 3p has, in the Bohr model, has a radius of about 9, and this has a radius of about 16. The square, it goes like n squared. So you have what's called a breathing mode. As you beat this coherent state, the 3p state with a radius of 9 expands to the 4p state with a radius of about 16, with a period of about, I'm forgetting now, but the period is it's around 6 femtoseconds, and you get this breathing mode, and that's reflected in the diffraction pattern. For the H2 plus linear superposition of the states here, we chose a fairly large radius, the same as Andre Baldrag chose, of around 6, where the slopes are not so great, and therefore the heavy particles. Yes?
There's a question. Sorry.
Yes?
Oh, sorry, just the previous slide. So did you assume that the so-called orientation of the nuclei?
We assumed that well, for hydrogen, you don't have an orientation. It's spherically symmetrical.
What are the two? Oh, okay.
For the next problem, I'll tell you. I will say about.
What are the two blobs? I'm sorry. What are the two blobs there? Then what's the spatial structure?
This is, we're plotting along the z-axis. So this is the scattering of the incident electrons from hydrogen. Some scattered this way, some scattered that way.
And how does like?
And this is the z-axis in the scattering plane. So you have your image, you have your target, you have the electron beam. The electron beam has some width, it scatters like that, and on the plane of scattering, this is what you observe. Well, no, this is what you observe. This is the way the target looks, the charge density of the target in the z-axis.
Okay. I see. Okay.
The direction on that was chosen by the excitation pulse, though, right? The
Yes,
alignment of the peak.
yes, yes. Yeah, the excitation was linearly polarized along the z-axis, and that determines. So here for hydrogen, we chose 6 AU separation, which is, and the referees insisted that we take into account variation, so we took 5% variation, which is much greater than what would normally happen in this state over the time period of our pulse. The alignment to the beam is 90 degrees, so we assumed that the H2 plus molecule is perpendicular to the incident electron beam, but with a spread of plus minus 20 degrees. And the beat period is 7.9 femtoseconds, so a 110 attosecond pulse can resolve electronic motion. This is what the charge density looks like. Here at t equals 0, one is on one nucleoside. As you increase to t over 4, the beat period over 4, you have a coherent superposition of electron density on both nucleosides, and then the electron hops to the right side, and then as you keep going, you get this again and back here. You see here that this varies in time. For this period, you can barely see there are minima. If we didn't do all this averaging that the referees insisted we do over the bond length, over the alignment angle, these are beautiful white lines here. It means this is two-slit diffraction, because the electron comes in, it sees two targets, and you get interference that cancels any amplitude in these regions, and that's visible here. Is there a minimum of the scattering there? But notice that in Born approximation, this scattering picture is identical to that one. It can't distinguish electrons on the left or the right. This is a problem with Born approximation. Yes?
I think I missed where you explained it, but how does the time resolution of the electron bunch come in? I mean, in the Born approximation, that's a plane wave, right?
Yes. So we have an electron pulse. We treat it as a wave packet, and we treat the scattering at each electron in our wave packet. So it's some spread of about 20, 30 eV, about 10 keV, and we treat for each energy as if it were a plane wave.
Okay, and then superimpose those to get
Yes.
your wave packet.
Yes.
I see, okay.
Okay, now that got into PhysRev letters. It got a lot of play. Peter Baum at Garking, who's one of the experimentalists working on such things, told me that paper greatly encouraged him because it indicated that his effort to try to get these short pulses would allow him to do good science. But the Born approximation, it has problems because it, as we said, it can't distinguish asymmetries. And so, given that you should be able to see something, we try to refine the theory and do a more proper theory, which is to look at coherent scattering. And we were motivated, this is the paper, it's a long paper, in which the theory is given. And we were stimulated by one of Francis Robichaud's paper, which I will quote in a few slides. Francis Robichaud told us that we were the first citation to his paper. So here is the scheme for ultrafast electron diffraction from a coherent state. I'm going to show you for the hydrogen atom, because when you deal with the coherent state, the calculations are much lengthier. We had to go to supercomputers and so on. But we still have 100 attosecond electron pulses, 10 keV. This is the bandwidth, this is the wavelength, a spread of 10⁻⁴ radians in the incident beam. and we're looking at hydrogen targets, I'm going to show you breathing modes, wiggling modes, and a hybrid mode. And the bottom line that I will conclude with is that these short electron pulses can image electronic motion despite the problems that arise. And the problems that arise is that if you want to treat the scattering properly, here's Francis's paper in 2000, and this is our paper in 2013. If you want to treat scattering properly, classically, you have a particle coming here, you have a target here. In Born approximation, you have a plane wave, which isn't localized anywhere. So the proper quantum wave, whoops, sorry. The proper quantum way to describe scattering is to treat both the target and the incident electron as wave packets. We have here a superposition of atomic states on the target. This is for the breathing mode I showed you, 3p and 4p. This would be just 2, n equals 3p and n equals 4p. There's a wave packet here for the incident electron with momentum k0, but spread around 10 keV by about 20 electron volts. The target also has a spread. So they're both localized because of this wave packet, and you have to sum over the momenta in these wave packets. That's your coherent wave function. And I don't want to go through the lengthy theory. It takes, I have about 20 handwritten pages of notes checking what my student Shao did. And the bottom line, however, with reasonable approximations, is very simple to understand. And let me emphasize this, that you want a differential scattering cross-section. Your superposition state is the sum over Cn with your target states n here, and they have a time dependence like that. T is what causes the interaction. In electron scattering, it's the electron correlation. For our hydrogen targets, it's the incident electron against the nucleus and the electron of the target. So you have to work out this transition matrix element. Then you go to some final state of the target and the scattered electron n. The coherent state gets summed coherently. Then you square this for transition to a particular final state that you can measure, and then you sum over all those final states. So this is the coherent state of the atom that comes into the right-hand side of this matrix element. And you can see that what the scattering process measures is this coherent state as probed by this interaction, which is the Coulomb interaction. And I'll show you that this actually relates. I want to plant in your mind this now. You can show that this relates to the momentum wave function of the target. So if you're trying to image target electron wave functions, it's the momentum space wave function that's important, as I'll show. So this is a picture showing you the breathing mode of this superposition 3p and 4p. I'm sorry, I didn't write the time dependence of the breathing mode. It's 5-something femtoseconds. But you see it expands and contracts, and whoops. And so now, I forgot to emphasize here. what this does here, this sum over m, is you have to sum over all final states within the 20 eV or so. 20 eV is a huge energy spread for hydrogen. It means all the Rydberg states can be excited in inelastic processes. And we had to work very hard to sum all these Rydberg states. We summed up to n equals 9, because once you get above n equals 9, you can use properties of Coulomb functions to simply, it's so close to the threshold to just integrate. And we ignored continuum states because if you ionize the hydrogen, then you could detect that experimentally. So what we had to do is to sum within the bandwidth of our pulse, electron pulse, all Rydberg states here. And this is different from when we did the elastic scattering and Born approximation from the state where we just were scattering from the charge density. So that's the complication when you do the scattering properly. Okay, I'll show you this. And this is the result you get. This is what the electron density is. This is, you've seen this before. So as a function of time delay, you have this breathing mode. The state is expanding. For a coherent state, it's very difficult to define what you mean by elastic scattering. But you could say, let's choose our final state m as 3p, or our final state m as 4p, because we start out with a linear combination of these, and so quasi-elastic scattering would be you end up on either one or the other. And that shows you a diffraction pattern, if you only count these two states, that changes with time in a way that's similar to what the electron density is. If you include all the inelastic processes, you can see some changes. Look, there's more of this color here than here. But you have to be more careful as to how you extract that. Here, this shows you different pulse durations. So most of the, fortunately for electron scattering, most of the inelastic processes happen at small angles. And so if you go to larger theta, and here we have as a function of theta, you can ignore most of the inelastic scattering that happen at very small theta. And you can then integrate for a fixed theta, you can integrate over phi, that's one way of doing it, or for a fixed phi, you can integrate over theta. This shows you the integration over theta. You can see here for different time delays, this is a log scale, so you have differences here between the differential probability. You have a 0 here, which is an image of your target, because this 0 comes from the 0 of the 3p wave function. 2p wave function in hydrogen has no nodes. 3p wave function has one node. The 4p wave function has two nodes. And we see in the diffraction pattern zeros due to all three of those nodes of the target wave function. So you're getting some imaging of the target. The higher nodes are at larger angles, theta equal 5. But there are three if one goes, but the cross-section is small. So I just point out this is the node of the 3p. This 0 is due to the node of the 3p. And then you have a reversal of the asymmetry with time. If you go to 500 attoseconds, well, the beat period is 5 femtoseconds, so this is still short enough to resolve that time dependence. You see that here. And my colleague Centurion claims that he will have 100 femtosecond electron pulses this year. So one is getting toward, most people have picosecond pulses, and getting to 100 femtoseconds has been a big experimental advance. If you go to 3 femtoseconds, however, this is the same order of magnitude as the beat period, and so you don't see much difference. There's still a little bit, but you're losing the resolution if you get there. Let's look at this. Robin Santra is interested in diffraction patterns for X-rays. So he has written several papers recently emphasizing also the importance of treating inelastic processes. In his case, it's Compton scattering processes for X-ray scattering. And
Excuse me,
yes,
to the electron part, I have two technical questions. So those electrons that are not scattered will give you like a Gaussian in the middle of your screen. So wouldn't that wash out the
well,
structure that you see
yeah,
here?
I mean, the interesting stuff happens at a fixed angle theta, and the beam that goes through is within 10 to the minus 4 radians or so.
So it's very tiny.
Yes.
And the second question is, how many electrons do you have per pulse? So is it like,
A good question. In our calculations, we assume 1 electron per pulse. A problem with electron scattering is that if you have many electrons per pulse, they repel each other, and that broadens your pulse. However, Ahmed Zaweel has made a big point in his papers that detection techniques are sophisticated enough that even if you only have 1 electron per pulse, you can detect the scattering. You just have to hope that you have high repetition rate to get enough counts. And there are ways to reduce the Coulomb scattering problem. One way to reduce the Coulomb scattering problem, and one that Matthias Fuchs and Martin Centurion at Nebraska are working on, is to make short pulses that have NeV energies, not KeV energies, because when you get to relativistic energies, the repulsion is less important. If the particles are moving very fast, just think about it. If they're spread a little bit, but they're moving 10 times faster, then even though the pulse looks broader, it goes through your target very quickly.
in the MEV case, you destroy the target much more, right?
In elastic scattering, you don't destroy the target.
So
The primary scattering is elastic, and the energy deposit is relatively little. And it contributes to the inelastic processes, which in electron scattering are confined to small atoms. Okay, so Robin never said how he produced these. You can't use a laser because these have 2 different parities. He just said, you know, let's produce these because you have this left-right asymmetry. And so he was using it for the electron scattering case and to show how you can observe this asymmetry. Because these have opposite parities, whoops. These have opposite parities and, stop. And so you get a flipping from one axis to another as they meet. They interfere coherently in one side and constructively and destructively. They're interfering and you get this asymmetry. The question is, when you do electron scattering, can you detect this asymmetry? Well, here is the electron density. It shows this asymmetry for different time delays here. These are the diffraction images. Here's our quasi-elastic results, which show you more clearly what's embedded here amongst all the inelastic processes. But you can see here, this is the diffraction pattern at 0 time delay is symmetric. This is asymmetric. It's asymmetric here at t over 4, whereas this is symmetric. At t over 2, this is symmetric. The electron density is asymmetric, so what's going on? The good news is that you're detecting the asymmetry now. When you treat this as coherent scattering, you can see in the diffraction pattern the asymmetry. That's the good news. Because in the Born approximation calculation, you don't see this asymmetry. You would get the same scattering picture. But the question is, how do we understand this difference at these time delays between the scattering pattern and what's happening with the charge density? Let me show you how you would observe in the full inelastic results. You observe these results. You take an angle theta that's away from most of the inelastic stuff and integrate over phi. That's what this gives you. And you can see here, look, theta equals half a degree. You integrate over phi. And these are 3 different time delays, the curves. This double dotted curve is the highest on the negative z-axis, on the positive z-axis, phi equals 0. And it's the lowest on the negative z-axis, which is phi close to 180 degrees. So the asymmetry is measurable, even including all this inelastic stuff. Now, you may observe that actually what will be done in the experiment is a hybrid electronic motion. Because if you try to populate, as I showed you before, the equal superposition of 3p and 4p, most of your amplitude is still going to remain on the ground state. So we call this a hybrid motion because, here I put the periods. I'm glad. If you look at the beat of the 3p and 4p, you get 6.25 femtoseconds. So that's a relatively slow breathing motion. But the 1s and 3p state and the 1s and 4p state they have opposite parity. So there's a fast wiggling motion with 300 something attosecond beat period. And so one should see both of those in this picture. So in this picture, this is the charge density. And so you can see this slow breathing mode, but very rapid back and forth motion. This slow breathing is going to go away. You see the asymmetry here. Whoops. And so now, if you have a 100 attosecond pulse, you should be able to distinguish both types of motion, both the slow breathing and the asymmetry. So you see here, for an angle of 0.5 degrees, these 3 different time delays, you have asymmetric curves with time delay. If you go to 500 attoseconds, which is longer than this fast wiggling beat period, you lose the asymmetry. These are symmetric curves. And if you look as a function of theta, you see here that as a function of theta, at t equals 1/8, you have, as a function of theta, this oscillatory motion, whereas here, for 500 attoseconds, you have a flat distribution. This is the difference. This is a measure of the asymmetry, as I'm glad Brett defined this in his lecture. The electrons scattered at 0 degrees minus electrons scattered at 180 degrees over the sum. This is normalized asymmetry. The slow breathing mode has no asymmetry. It's symmetric. So these cancel and you get 0. And if your pulse is 500 attoseconds, you don't detect this asymmetric fast wiggling. And so the asymmetry is absolutely 0 here, whereas the asymmetry for 100 attosecond pulses is definitely there. So now I want to finish with how one can improve upon ultrafast electron diffraction, including inelastic processes, by doing some energy resolution of the results. And here, this is our proposed experiment. You have electron pulses, you have a laser that sets up in some target, some coherent state, you set in motion some process. And then after a time delay, you hit it with the electrons, and the scattered electrons are then sent through an energy analyzer, and you distinguish the scattering picture, you distinguish, or you measure the energy of the scattered electrons. Here is a picture of our electron pulse profile for 3 different full-width half maxima of our pulses. So all of these pulses have 10 keV energy. This is a 100 attosecond pulse, 500 attosecond, 3.13 femtosecond pulse. The angular width is 10 to the minus 4 radians. It's the same for all pulses. But the energy bandwidth changes. For 100 attoseconds, the bandwidth is 18.2 eV. So that gives you this spread on energy, so the incident electrons. For 3.65 bandwidth, you have a smaller spread. This is the projection on the lower plane of this. And for 0.5 eV, you have essentially monochromatic pulses. And that's what it looks like. And now this is what you get for the breathing motion of the 3p and 4p states. For 100 attoseconds, you see it looks like there's almost no difference for different time delays, 0t over 4t over 2. For 500 attoseconds, you see 2 peaks here with different time-dependent behaviors. These 2 peaks, it turns out, are inelastic. This peak here is an energy greater than 10 keV, and it's greater than 10 keV by the inelastic process that you de-excite the coherent state, 3p, 4p, to the 1s state. So by de-exciting the energy of the target, the incident electron scatters with higher energy. And so this is above 10 keV. Other inelastic processes involve excitations from 3p to 4p to higher Lindbergh states, and so you lose a certain amount of energy in your pulse, and that's the bulk of this. If you go to 3 femtoseconds, again, there's almost no time change with time. So 500 attoseconds looks like, and energy resolution looks like a good way of detecting the breathing motion of the state. So for a 500 attosecond pulse, if you measure the results of de-exciting the target to the 1s state, you see these diffraction patterns in your scattering plane. Notice that as the time increases, the breathing mode is expanding. And because you scatter most easily from tightly bound states, you get most of the scattering when the target state is the smallest. And as it expands, the de-excitation to 1s decreases, and you get lower scattering. So by measuring the 1s state, you detect the breathing motion, but it's greatest when the target is most compressed. And these are the inelastic processes. You see they're confined close to 0 degrees. This dotted line indicates the most heavy population of inelastic processes. Outside that line, you can see changes slightly. And now, so this is 500 nanosecond pulse. This is phi equals 0. That means positive z-axis, 0 time delay, negative z-axis, 180 degrees. This is the de-excitation to the 1s state. This is everything else. And now, as you go to t over 4, 3t over 4, what we did was take our calculated data for the scattering here and subtracted the data you have at 0 to increase the contrast between 0 time delay and the time delay at t over 4. And now you see here clearly, here the majority, the black is more intense here. You have most of the state on the left. Here it's on the right. So your measurement of the 1s inelastic process shows you the asymmetry of the fast this is the wiggling motion of the 3p and 4d states. Sorry, I've changed states here. So this is the wiggling motion of 3d and 4p, which are asymmetric. You get this scattering pattern, you subtract it from the data for t over 4, and you see the asymmetry of this wiggling mode. And this shows you if you integrate over phi for a fixed theta equals 0.3, 0.5, 1, or 1.5. Let's look at 1.5 degrees here. You can see here the dashed line is the lowest at phi equals 0. It's the highest at 180. So you are able to detect the asymmetric motion of this wiggling mode of 3D, 4P, 4F. Or is it 3P, 4D? I forget. It's 3D, 4F state. And so I want to finish the lecture with pointing out that the momentum perspective is the one to take when you do electron scattering. This is the differential cross-section, as I've explained before. One has to still work out this transition matrix element from each end state of the coherent superposition to some final state of the target. In Born approximation, this transition matrix element looks like this, where V are the Coulomb interaction with the nucleus and with the 2 electrons. This can be worked out analytically for hydrogen. And for hydrogen, if you substitute this result in here, you get this. And so you have a Fourier transform of the coherent superposition state with the inelastic final state of the target. You can do a convolution integral. Sorry, it's not a Fourier, it's a convolution integral of this. You can do this integral, and what you get is the overlap of the momentum state of your coherent superposition with the momentum state of your final measured target. And so it's the momentum state of the coherent wave function that is reflected in the differential probability. Just to give you an example here, you have the incident electron. It exchanges momentum with the target and goes off with Ka momentum. So this is the momentum transfer, and the differential cross-section is proportional to the overlap of 2 momentum wave functions. And this shows you the wave function in momentum space. This is the real part, the imaginary part, because these are complex amplitudes. But if we take the coherent state and square it, you can see that at the time delay, say, of t over 4, this momentum is negative along the z-axis, very small positive component here. So it's asymmetric. And at T over 4, the charge density for the 3D 4F state is neutral, but you can see that this is moving, the amplitude is moving to the left, because at T over 2, this is where it ends up. So your momentum wave function at T over 4 reflects what this state is actually doing in momentum space. It's actually moving that way. And these momentum wave functions are consistent with what you observe in the scatter. Because this shows you here that at T over 4, you have predominantly in the negative z-axis. This is what you observe, and that's what this momentum wave function is largely. And let me finish. So I hope I've shown you that ultrafast electron diffraction depends on the target wave function, not the target charge density. The target charge density can't show you the asymmetries, and the time dependence is not consistent with the observed scattering differential probability. It's the target momentum wave function is what gives you the most insight into what you're observing. And I've shown at the end that energy-resolved ultrafast electron diffraction can ameliorate some of the problems with all these inelastic processes that come in and participate when you have a bandwidth pulse that you have to take into account. And these are references. This is our description of the theory, and this is the description of the energy resolve process. And you should see also this result for time-resolved ultrafast electron E2E momentum spectroscopy. This was pointed out by Lars Madsen to us in 2011, I think, that the E2E process measures the momentum wave function of a target. And sure enough, when we did the calculations, you could understand the scattering phenomena if you do an E2E measurement in terms of the momentum wave function of your target. Or I should say your scattering is proportional to the momentum wave. But in this calculation, we did not take into account inelastic processes. We did hydrogen, which has no inelastic processes if you measure both electron energies. But for a general target, you would have to take into account inelastic processes, and so I didn't present this here. With that, I'll finish.
Thank you. Questions?
So when people make these electron pulses, is
Yes.
there any known method to measure the pulse duration?
Is there any known method to measure the pulse duration? Well, as I said, they have these, they excite from a metal tip electron pulses, and the laser that does it, sapphire laser, you shine it on a metal tip, and you get a burst of electrons every cycle. The electric field points in one direction every cycle, and so that wave packet is 2.7 femtoseconds or so. And then they have this thin lens formula for telling you where you get the minimum wave packet on your target. And, so they have an upper limit on the initial wave packet, and then they can minimize the duration on the target. As long as they're much lower than the beat period or the time period of whatever electronic motion you're trying to measure, and it'll be okay. You don't have to know precisely.
You know, but I mean, so you can know that, okay, this electron pulse is